Now I got. Okay, so last class I hope we have covered up to conditional, right?
Sir, implication.
Sorry.
Implication.
Implications.
Sir, implication.
Yes, that's what I asked. Conditional. That means it is implication. Conditional statements are covered. Well, there are as I said, there are I guess 14 equivalent statements of conditional. You can use it by if, then, when, necessary conditions, sufficient conditions. All those forms are there. Let us discuss one more connective, which is biconditional, or sometimes it is called double implication. Okay, let me share the screen with you. I guess the Jamboard is visible.
Yes, sir.
Okay, so today we'll start with biconditional. Suppose we have two statements P and Q. Let P and Q be two propositions. The biconditional of P and Q, it is written by this symbol, written as P double implication Q. It is a symbol for biconditional. Now it is a statement, is a proposition that P if and only P if and only if Q. This is the proposition that biconditional of P and Q. It is P if and only if Q. Or sometimes it is written by like this P IFF. Whenever you see this IFF, this is if and only if. Either it is in this form P if and only if Q or P IFF Q. It is if and only if. Now the biconditional statement, the truth value of the biconditional statement of the statement P double implication Q is false when exactly one of them is false, otherwise true. Okay. This is the truth value of the biconditional statement P double implication Q. Now it is false when exactly one of them is false. When exactly either P or Q is false, then it is false. Otherwise, it is true. If you look at the truth table of the biconditional, suppose we have two propositions P Q, and this is for P double implication Q. P biconditional Q. Here it is P, Q, and this. And we have four choices for that. True, 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 false, false, true, false, false, right? Now, when exactly one of them is false, I mean, in these two cases, here it is false, and here it is false, and in all other cases, it is true. This one it is true, and this is true. Okay. When exactly one of the statements is false, then it is false. The biconditional. Well, if you compare this, with the exclusive OR, if you look at the truth table of exclusive OR, it's sometimes exactly opposite of the truth table of exclusive OR. So the exclusive OR said that when one of the statement is true, then the truth value is true. Okay. So in this case, it was exactly true, and in all other cases it was false. But this biconditional is exactly the negation of exclusive OR. So this P double implication Q, this statement is equivalent to the negation of P exclusive Q. Okay. So that will discuss the equivalence of statement. We will discuss later on. But just for your information, I am saying that it's exactly opposite of the exclusive OR. Okay. Well, as I told, we use if and only for representing a biconditional statement. But in general practice, we are not. Uh, I mean, we do not use if and only in general English language, unless it is a mathematical statement. For example, suppose I'm saying something. If you finish the dinner in the table, then you can go for the dessert. No, it's a general statement, general English, but it is used in biconditional sense. That if you finish the dinner, then you will go for the dessert. It is used in a biconditional sense. In general practice, this is avoided, but in mathematics, we use it very often. For a theorem, when both the conditions are satisfied, then we use this biconditional statement. Let us take this example. So suppose the statement P is that you can take a flight and the statement Q is you buy a ticket. Okay. Then the P biconditional Q, this statement is you can take a flight if and only if you buy a ticket. So that means this statement can be understood in this way, that if you take a flight, then you buy a ticket. If you buy a ticket, then you can take the flight. That's the meaning of biconditional. It is true in both the way. Okay, there are also equivalent statements of biconditional. P biconditional Q can be represented by these equivalent statements. Okay. So as I told, it can be represented by P if and only if Q. So this one is Q. Or we can write P is necessary and sufficient for Q, or we can write if P then Q, and conversely. The fourth equivalent form is P exactly when Q. Okay, these are the equivalent forms of biconditional. So either you can write in this form P if and only if Q, or you can write P is necessary and sufficient for Q, if P then Q, and conversely. So this word conversely means if Q then P. That's what the meaning of the converse statement. That we'll discuss also later on. P exactly when Q. That means when P is, this is if P then Q, and if Q then P. That's what the meaning exactly when Q. There are four equivalent statements of biconditional. But if you look at the conditional, there are 14 equivalent statements. Okay? In any of the form, you can see a conditional statement, an implication that if P then Q, Q if P, Q whenever P, and so on. All those statements, equivalent statements of conditional. Well, for biconditional, you can see any one of these forms. Okay. Well, okay, that will discuss after discussing the equivalence of statements. Okay. So till now, what we discussed, we can form compound statements by using connectives, and we have discussed the connectives up to 5 connectives like not, and, or, exclusive or, conditional, and biconditional. These connectives we have already discussed. For not, the negation one, we need a single statement, and for all other things, conjunction, disjunction, exclusive or, implication, and bicondition, we need at least 2 statements to form a new compound set. Okay. Well, this can be extended to as many as number of statements as you want, right? And the truth table can be constructed one by one. Okay, next is the tautology. Tautology fallacy, we'll discuss that. Now, what's a tautology? A tautology is a compound statement which has truth value always true, whatever the truth values of the atomic statements are. If the truth value of a compound statement is always true, irrespective of the truth values of the atomic statements, then that statement, that compound statement, is called a tautology. So let me write that a compound statement that is always true no matter the truth values of the propositional variables. That occur in it is called a tautology. Okay. So, a compound statement can be formed by 2 or more atomic statements. The atomic statements, they have truth values. They can be true, they can be false. But irrespective of the truth values of the atomic statement, if the compound statement has truth value which is always true, then that compound statement is called a tautology. And similarly, let me first take some examples of tautology, then I'll go for the other one. For example, so let us consider this statement: P or negation of P. Let's take this statement. P is a propositional variable, and we are finding the disjunction of P or negation of P. Let us make a truth table for that. Suppose I have the propositional variable p here and negation of p here. Then at last I will find this one p disjunction negation of p. Okay, then I have two choices for p. P can be true, p can be false. Now, if I have these two choices for p, what will be negation of p?
False and true.
It is false and true. Well, how about the disjunction? P or negation of p? What will be truth value of this
True and true.
one? Because the disjunction is false when both the statements are false. Otherwise, it is true. Right? Now here, look at this values. Look at the values of the last statement. This column. Okay. You can see that whatever the truth value of this statement P and negation P, it always gives a truth value. P disjunction negation P is always true. Okay. Now this statement P disjunction negation P, so you can say P disjunction negation P is a tautology. Because irrespective of the truth value of P and negation P, this compound statement, it is a compound statement, no doubt with that. This one is a compound statement because it is constructed from an atomic statement P, and we are finding the disjunction of P and negation of P. Irrespective of the truth values of P and negation of P, this compound statement has truth value true always. Okay. Hence, it's a tautology. Now, you might be thinking that what happens? Is it possible that there are
Sir,
yeah?
sir, disjunction is between the two statements. Then here, why one statement is there?
I have taken two statements. Like P is a statement, negation P is also another statement. Don't confuse with that. P is a statement. Now, if I am taking negation of P, this is another statement. This is not same as P, right? Or still you are getting confused.
No, sir, got it.
Yeah. In fact, you can also find the disjunction of P or P. No doubt with that. I mean, although both are the same truth value P, this is equivalent to P, but we can construct that. Here I have taken, if you look at the definitions of disjunction or conjunction, whatever I have taken let P, Q be two statements. So there I have not taken that let P, Q be two different statements. I have not taken that. I have taken that two statements. They can be same. Well, now, as I was saying, that you might be thinking of that, is it possible that the truth value of a compound statement could be always false? Is it possible? And the answer to that question is yes. There are statements for which the truth value is always false, irrespective of the truth values of the atomic statements. Okay, and those kind of statements, they are called contradiction or fallacy. So let me write that. It's contradiction. Or sometimes it is called fallacy. What are the statements? That a compound statement that is always false is called, well, here I am not writing the fact that irrespective of the fact that the truth values of the atomic statements. So it's all, when it is always false, it's called a contradiction. Yeah, or it's a fallacy. Well, let us take an example. that does there exist some statements which is always false. If I am taking say P conjunction negation of P, no doubt is this statement P conjunction negation P is a compound statement. Let's construct the truth table for that. Here I am taking P, this is negation of P, and the last one is P conjunction negation of P. This P negation of P, P conjunction negation of P. Now for P, I have two choices, true, false. The negation of P will be false, true. Now how about this conjunction? When the conjunction is true, and tell me, when the conjunction of a statement is true,
So when both of them are true.
when both the statements are true. Good. But here you can see that none of the statements, here it is true, false, and here it is false, true, right? So the conjunction of this statement, the two statements, that will be false as well as here it is false. Okay. Now if you look at the truth values of the last statement, this conjunction of P and negation of P, it is always false. Look at the last comment. It is always false, irrespective of the fact that whatever the truth values of P and negation of P, the truth value of P and negation of P is false always. Hence, you can say the statement P and negation of P is a contradiction. Okay. Now there are statements which cannot be always true, which are not always false, and those kind of statements are called contingency. Now, what is a contingency? That a compound statement that is neither a tautology nor a contradiction. That is neither a tautology nor a contradiction. Is called a contingency. Okay. Compound statements that categorized into three categories. Some of them they are tautologies, some of them they are contradictions, and the rest ones, which are neither contradiction nor tautologies, they are called contingencies. Okay. Let us take some more examples. For example, if you look at this P implies Q. Example, say P implies Q, P conjunction Q, P disjunction Q. These are the examples of contingencies. Okay, because they are neither tautologies nor they are contradictions. That is, for some values of truth values of P and Q they are true, and for some other values they are the truth value false. Okay. So they are contingencies. Okay, as we have implication and we discuss about the biconditional, now we can think of the converse. What is the converse of an implication? So there are more statements can be constructed that converse, inverse, and contrapositive. That there is also new way of constructing compound propositions from the existing ones, from the existing propositions. Converse. So here what I am doing, the converse, inverse, and contrapositive, I am doing for the implication statements. Converse of an implication, inverse of an implication, and contrapositive of an implication. So here you can say that we can construct new conditional statements from the existing P implies Q, from the existing conditional P implies Q. So we can form new conditional statements. new conditional statements from P implies Q, and one way is converse. The converse of P implies Q is Q implies Q. This one is a converse. The converse of P implies Q is Q implies Q. Now the inverse of P implies Q is negation P implies negation Q, and the contrapositive of P implies Q is negation Q implies negation P. These are the three new conditional statements that can be constructed from this existing P implies Q. The converse, inverse, and contrapositive. Because what happens? See, when we're going to prove some mathematical statement, sometimes proving the direct conditional statement might be a hard task. So in those cases, we can go for its proof for the contrapositive case. That P implies Q is equivalent to negation Q implies negation. But all these two, they are not equivalent, but P implies Q is exactly equivalent to negation Q and negation P. Okay, so in those cases, this contrapositive is useful. That when the direct implication is hard to prove, then you can go for the contrapositive proof. Now, how this converse, inverse, and contrapositive, what are the truth values of that? So let me construct a big truth table, and I'm writing the truth values of all those statements, converse, inverse, as well as. Okay, so I'm writing the statements P, then Q, negation of P, negation of P, Q, then I have P implies Q. This one is a converse. Q implies P. Okay, then I need to make a bit less. Here I'm writing it as negation Q implies negation P. I'm constructing the truth table for all these statements. Okay, so I need one more, inverse. P implies Q is there, it is converse, it is contrapositive. I need one more, maybe the last one. So this one I'm writing for negation P implies negation Q. Okay, so this one is a converse, this one is a contrapositive, and the last one is the inverse. Well, since I have two statements, I have four choices for the truth values. That both can be true, both can be false, and one can be true, the other can be false. So it is true, 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 false, false, true, and false, false. Now tell me, what is negation of P? What will be this column?
False. False, true, true.
False, false, true, true. Then negation of Q.
False, true, false, true.
False, true, false, true. How about P implies Q?
True, false, true, true.
True, false, true, true. Now, what is converse of this?
True, true, false, true.
Very good. True, true, false, true. What is the contrapositive?
True, false, true, true.
Okay, contrapositive is this negation Q implies negation first it is true, and this one will be false. This one will be true and
True
true, right?
and true.
Yeah. So when you find this contrapositive, you need to look at these two columns because it involves the negation of P and negation of Q. Then how about this inverse? Negation P implies negation Q. Now tell me, what is the inverse?
It will be the converse only.
It might be the converse only. How? It is negation P implies negation Q, right? So here I have false and false. Now in this case it is true. False, true. It is
True, false, true.
true. It is false,
True.
true.
And true.
So is it same as the converse?
Yes.
Okay. So now from here, if you can mark two things, look at these values. That this column, this converse part, it is exactly equal to the inverse part. Right? Converse part is exactly equal to the inverse part. However, if you look at the other two, this implication, P implies Q, this column is exactly equal to the contrapositive. Right? So, here from this truth table, we can say that these two columns, these two statements, they are equivalent, and these two statements, they are equivalent. So, now what is the definition of equivalence of two statements? That we say two statements are equivalent in a precise way. So, equivalence of statements. Equivalence of statements. Equivalent statements. When two compound statements or compound propositions always have the same truth value. Always have the same truth value. Regardless the truth value of the propositional variables when two compound propositions always have the same truth value regardless the truth values of the propositional variables are called equivalent propositions. Equivalent propositions. Okay, that's the definition of equivalent proposition. That when we say that two propositions are equivalent or two statements are equivalent. Now, regardless the truth values of the proposition variables, now here you can verify that the contrapositive, this column, and the implication P implies Q. Now, whatever the truth value of P and Q, these two compound statements, the truth value of these two compound statements, they are equivalent. Now, when both P and Q are true, then P implies Q is true, negation Q implies negation P is also. When P is true, Q is false, P implies Q is false, negation Q implies negation P is false. And when it is false and Q is true, it is true, this one is true. And when both are false, implication is true, as well as this contrapositive is true. So, irrespective of the truth values of the propositional variables, you can say these two statements, P implies Q and negation Q implies negation P, that is the contrapositive part, they are same. The truth values of these two compound statements, they are same. So, here I can say that P implies Q, this compound statement is equivalent to negation Q implies negation P. Okay. So, since these two compound statements are equivalent. So whenever we want to prove some implication, if it is hard to prove the direct implication, in those cases we prove by using the method of contraposition. And in some sense, this part will be easy, the method of contraposition. Now, similarly, if you look at the converse statement, this compound statement is exactly equal to the inverse one. So Q implies P. It is equivalent to negation P implies negation Q. Okay. So these are two examples of two compound statements which are equivalent. This is a compound statement, this one is a compound statement, and they are equivalent because both have same truth values, irrespective of the truth values of P and Q. Similarly for the converse one. Okay. For example, let us take another equivalent statement. So here I am saying P implies Q. It will be equivalent to negation P or Q. Negation P, disjunction Q. And I am saying these two statements, they are equivalent. Now how to verify? We will verify this by truth tables. Let us go for the truth table. Okay, so I have two propositions P, Q, and what else I need? I need negation P. Then I need P implies Q. At last, negation P, disjunction Q. Okay. Well, for two statements we have four choices: true, 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 false, false, true, and false, false. Okay. Negation P will be, this will be false, false, true, and true. Now what is the implication?
True, false, true, true.
True, false, true, true. Now how about the disjunction? Negation P or Q. Now here you have to take these two columns, negation P and Q. How about this disjunction? When this disjunction is false and when it is true.
False, false, true, false.
Are you sure?
True, false, true, true.
Because the disjunction is false when both are false, right? So in this case only. In this case both are false. In this case only it will be false. And in all other cases it is true. Right? Now look at these values. Look at the last two columns. These two compound statements, they have same truth value. True, true, false, false, true, true, true. So irrespective of the truth values of this P and Q, these propositional variables, they have same truth value. Hence, these two statements are equivalent. So whenever it is asked that verify the equivalence of these two statements, now you can go for the truth table and you can check that these two compound statements, they have the same truth value. Okay. Similar thing can be drawn for this one, that P double implication Q, the truth value of this statement, of the compound statement, is same as P implies Q and Q implies Q. This compound statement is equivalent to this compound statement. Okay. Well, the same way we can go for the truth table test. So let us write that. I have PQ. What else I need? I need P implies Q. I need Q implies P. And then I need the conjunction. P implies Q. Conjunction Q implies P. And at last I'm writing a P double implication Q. I have P Q here. Okay, so I have this choices: true, 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 false, false, true, and false, false. Now tell me, what is P implies Q?
True, false,
True, false, true, true.
True, false, true. What is Q implies Q?
True, true,
true,
false, true.
false, true.
True, true, false, true. How about this conjunction of these two statements? Now,
So, true, false, false, true.
true, false, false, true.
False, true.
Good. How about this implication, double implication?
True, false, false, true.
Yes, true, false, false, true. Okay. Now, from here you can verify that these two compound statements, they have the same truth value. Okay. Now this gives the proof for the equivalence of these two statements. That P double implication Q is exactly equal to P implies Q and Q implies Q.
Excuse me, sir.
Yeah.
Can you explain the double implication first?
Sorry, you're not audible clearly.
Sir, can you explain the double implication part?
Yes. Double implication, I just told, right? Let me show the slide to you. That the double implication is false when exactly one of them is false. In the first slide, just there. Here. This one is the truth table for double implication. When both the statements have same truth value, then it is true. And when both have true, true, then it is true. When both have false, false, then it is true. And in all of the other cases, it is false. Or in fact, if one statement is true and the other one is false, then it is false. That is the truth value of double implication. Okay. Okay, there are so many equivalence statements. In fact, if you look at your book, there are maybe I'll give you two more. You need to verify this that prove that the following statements are equivalent. Following statements are equivalent. The first one is, say, negation of P or Q. It is equivalent to negation P and negation Q. The second one is negation of P and Q. It is equivalent to negation P or negation Q. This two are homework for you. Throw two table, try to prove these two statements. And these two equivalent statements, they are called De Morgan's law. So just go through the truth table and show that this compound statement has same truth value as this compound statement, and this compound statement has same truth value as this one. Okay, that's it for today. Let us take the attendance. Maybe sharing this in the classroom. Jam note is there in your classroom. You can have a look.